What if I told you a humanoid robot just did the dishes in a real kitchen? Not as a staged demo, not remotely controlled, and not following a pre-written script, but fully autonomously, start to finish. And while you're watching it unload plates and cups, a bigger question quietly appears in the background. Is it checking whether those dishes are actually clean? How does it avoid cross-contamination? And more importantly, how close are we to robots that can actually help us in everyday life? Today, we're taking a deep look at Figure 03, powered by Helix 02, and why this recent set of demos may be one of the most important moments in humanoid robotics so far. Let's start with the kitchen demo, because this isn't just about washing dishes. This 4-minute sequence is believed to be the longest, most complex, fully autonomous task ever completed by a humanoid robot in a real environment. No teleoperation, no resets, no human stepping in when things go wrong. The robot walks up to a real dishwasher in a real kitchen. It opens the door, reaches inside, identifies plates, bowls, glasses, and utensils of different shapes and sizes. It carefully removes them one by one, carries them across the room, places them onto shelves, and stacks them correctly, all while maintaining balance and avoiding collisions. At one point, its hands are full, so it uses its hips to close a drawer. Later, it uses its foot to lift and close the dishwasher door. That detail matters more than it seems, because it shows the robot isn't just using its hands, it's using its entire body as a tool, just like a human would. By the end of the demo, Figure 03 reloads the dishwasher and starts it. In total, this involved 61 distinct manipulation actions, performed continuously, with zero human intervention. What makes this even more impressive is why it works. Earlier versions of Figure System, like Helix 1, controlled mainly the upper body. Helix 02 is different. It uses a single unified neural network to control the entire robot, walking, balancing, reaching, grasping, and manipulating, all at once, based purely on raw sensory input. That means there are no separate systems handing off control to each other. Everything goes in vision, touch, body position, and everything comes out, joint movements, balance adjustments, fine finger motions, through one continuous visual motor brain. This all sensors in, all actuators out approach is why the robot moves smoothly instead of with the jerky, segmented motion we usually associate with humanoids. Underneath that is Figure's 3-system architecture. At the foundation is what they call System 0. This is the layer responsible for human-like, whole-body movement. It was trained on over 1,000 hours of human motion data, learning how humans naturally walk, lean, crouch, reach, and balance. Instead of engineers manually designing rules for walking or turning or reaching, the system simply learns to imitate human motion directly. It runs at around 1,000 updates per second, constantly adjusting posture and balance in real time. And the key thing here is that all of this was trained in simulation across hundreds of thousands of parallel environments, allowing skills to transfer directly to real robots with minimal adjustment. That's why Figure 03 can smoothly shift its weight while carrying plates, bend down to place soap, or lean forward without losing stability, even when the environment changes. But the real moment where Helix 02 separates itself from previous humanoids is in Dexterity. Let's talk about the bottle cap demo. Unscrewing a bottle sounds simple, but for a robot, it's brutally difficult. One hand has to stabilize the bottle. The other has to apply just the right amount of torque. Too little, and nothing happens. Too much, and the bottle collapses or slips. Helix 02 handles this using bimanual coordination combined with tactile feedback, constantly sensing grip force and rotation resistance as it twists the cap off smoothly. Then there's the pill-picking demo. Here, the robot has to extract a single tiny pill from a medicine organizer. The pill is partially hidden, meaning it's not fully visible from the robot's head camera. Instead, Figure 03 relies on palm-mounted cameras and tactile sensors in the fingers, allowing it to see and feel what it's doing at extremely close range. It adjusts its grasp in real time, applying just enough pressure to pick up the pill without dropping or crushing it. Next comes the syringe demo, and this one is easy to underestimate. The robot is asked to dispense exactly 5 milliliters from a syringe. As the plunger moves, resistance changes. This means the robot can't just push blindly. It has to continuously sense force, adjust pressure, and stop at precisely the right moment. This requires force-controlled actuation, tactile feedback, and coordinated multi-finger stabilization. Essentially the same kind of control you'd expect from a trained lab technician. And finally, we see the robot sorting metal pieces in a cluttered environment. The objects overlap, shift when touched, and partially block each other from view. Pure vision isn't enough here. The robot has to identify which pieces are graspable, confirm contact through touch, and adjust its grip as objects move. Figure 03 successfully extracts individual metal parts and transfers them between containers, a task directly relevant to manufacturing and logistics. Now, here's what's easy to miss if you're only watching casually. The same neural network is controlling millimeter-scale finger movements and room-scale walking movements at the same time. It's coordinating both arms together continuously. It's recovering from small errors without stopping or resetting. And it's maintaining task awareness across minutes-long sequences. This matters because for decades, robotics has struggled with a fundamental problem. Walking is hard. Manipulation is hard. But doing both together is exponentially harder. When a robot lifts an object, its balance changes. When it steps forward, its reach changes. These interactions resist being broken into clean, separate modules. Helix 02 doesn't try to decompose the problem. It treats the robot as a single embodied system, just like a human body. And that's why this demo isn't just impressive, it's meaningful. This isn't a robot doing a party trick. It's a robot showing the foundations of real-world usefulness. Kitchens, labs, factories, homes. So the real question isn't whether humanoid robots are coming. That part is already decided. The real question is how fast systems like this move from carefully controlled demos into everyday environments where nothing is staged, nothing is predictable, and mistakes actually matter. Because once robots can walk, see, feel, adapt, and recover from errors on their own, the line between a demo and a useful assistant starts to disappear. A kitchen turns into a testing ground. A lab turns into a workplace. And eventually, homes and factories stop being special cases. And when that moment arrives, we're going to face a choice. Do we live alongside fully closed, proprietary humanoids that work perfectly? Or do we push toward more open, customizable systems that give people control, transparency, and flexibility? So I'm curious, which future sounds better to you? And what's the first task you'd actually want a humanoid robot to handle in your daily life? If you enjoy deep dives into real, practical AI and humanoid robotics, not hype, make sure to like, subscribe, and stay tuned.